All righty, friends. Hello, hello, hello. Welcome back. We're going to continue working our way through a little bit of calculus now. And we've talked about this idea of discontinuity, when things are discontinuous. Well, if things can be discontinuous, means they break, that means there's something to do with continuity, with things being continuous. So that's going to be kind of what we talk about today. So today is about continuity. Well, that's not what I apparently have fat fingers. There we are. Continuity and one-sided limit. So this is going to be the gist of what we're looking at today. So let's take a look at a graph and see if we can't figure out, first of all, about limits, because continuity is based off the idea of a limit. So we need to dive just a little bit more into what a limit is. I mean, we're pretty close. We need to know just a little bit more. So let's say we have a value here. We'll call that C. And we'll call this L right here. Okay, we'll make a hole there. And let's go ahead and make our handy dandy little graph like that. There we go. All righty, so continuity is built on functions being defined and limits existing. Well, function being defined, that's what we've been doing our entire mathematical lives. You plug a number in for f of x, you get a value. If you get a value, the function is defined. So what we need to talk about is a limit existing. And already we've said that a limit exists when the graph approaches from the left side, which we call the negative side because this is negative infinity, and the right side, like that, they approach the same value. We call this the positive side because that's positive infinity. So left side is negative infinity, right side is positive infinity. Now we say that this limit exists when we'd say that the limit of x approaches c, we say that this exists. I guess I probably should have labeled that green graph as being f of x. It exists when two things are equal. So we've said when the graph approaches the same point, but we want to be a little bit more specific. So in math, we say, well, if the graph is approaching from the left side, we say that that's approaching the x value, that c value, from the negative side. We say then that this is equal to this. So if I want to prove that a limit exists, then I got to show that the limit from some number from the negative side equals the same value if I approach it from the positive side. So what this means then is right here, this idea is a limit. Well, this right here, so we call that just a regular old limit. But these right here, these are called one-sided limits because they're only dealing with the graph coming from one side. So one-sided limits. So a graph, if it just says limit, then that means it has to approach from the same value from both sides. But if it has either this little negative or this little positive, that would be a one-sided limit. So approaches from the negative side or the left side, approaches from the positive infinity side or the right side. And I'm going to write f of x on here because that bugs me. So we're talking about this idea of a one-sided limit. And we need to have a kind of a basis on that. in order for us to be able to talk eventually about what continuity really is. What makes something continuous? So let me go ahead and give you one of my favorite graphs here. So, funky looking graph. And for my graph, let's do this one in red. I'm going to say that it has an open dot here at -1 and an open dot here when y is +1. And let's go out here with it. This graph right here is the graph, or is the function, f of x equals the absolute value of x minus 3 over x minus 3. So just wanted to throw on one of these little absolute value kind of step functions here. But it gives us the idea to be able to talk about if a limit exists. So we're going to evaluate a couple limits here. We'll evaluate this from the negative side. We'll evaluate this from the positive side. And we evaluate it from the regular side. Or not regular side, but the original limit itself. So we're going to have two one-sided limits here, and we're going to have a normal limit. So first up, from the negative side. So that means I'm going to start from the negative infinity side, and I'm approaching it from that direction. So I'm coming from that direction. So if I approach 3 from that direction, I go to the value of -1. This one right here is if I were to approach from the positive infinity side. So here's positive infinity. This says I'm approaching it from the positive infinity side. And that would have gone to +1. So negative is approaching from the negative infinity or left side. Positive is approaching from positive infinity or the right side. But now on this last one, I'm asking, what is it just when x equals 3? Well, if you notice, since these two right here aren't in agreement, they're not the same, that means even though we can find a one-sided limit, we can't find the actual full limit. So we'd say that this does not exist. And it's not good enough just to say that it doesn't exist. In calculus, we want to be really careful to always give a reason. So we're going to give a reason. So it does not exist because and we're going to say why. Why we believe that in taking this stance for us saying and having and forming our opinion. So we believe that this does not exist. And the reason why we come up with that statement, so we're going to explain our reasoning, is because the two one-sided limits don't agree. So in calculus, you got to remember, a lot of it is dealing with reasoning. So it's not so much to get the right answers, but it's can you create or give a reason for your answer? It's always about reasoning. So they don't exist, and they don't exist because the limits, the one-sided limits, aren't equal. Well, let's have you guys try, maybe instead of a graph, maybe let's try this with an equation type way. See what you guys come up with this. What if I give you something like, oh, let's let f of x be equal to the absolute value, not absolute value, I lied, piecewise, where the one piece will be x minus 1, and that's when x is less than 1. And the square root of x minus 1. And that'll be when x is greater than 1. So here's what I want to know. I would like to know the limit as x approaches 1 from the negative side. I'd like to know the limit as x approaches 1 from the positive side. And after that, I would just like to know the limit. All righty, so why don't you guys go ahead and pause the video and solve that down real quick, and we will talk about it. And let's see what we came up with here. From the -1 side. So that means the negative side, that's when it's less than, or from the left side, that means I'm dealing with, on this one, I'm dealing with that particular piece. So I'm going to go ahead and plug that in there. Notice how I brought the limit notation with me. So I'm going to be taking the limit of x minus 1. So 1 minus 1 is 0. The next part, from the positive side, that's when it's greater than. So that means I'm dealing with this one for the positive side. So we plug it in here. And I'm dealing with the square root of x minus 1. So square root of 1 minus 1 would be 0. And now, there is no one-side limit here, so I look at the two limits. Can I evaluate it? And in this case, I can. So I could say it equals 0, but again, I have to give a reason for it. Why do I believe that it's 0? Because the limit as x approaches 1 from the negative side, that equals 0, which is also equal to the limit as x approaches 1 from the positive side. So it's, again, yes, I can get the answer and I can say it's 0, but I have to supply the reason behind why I believe my answer is what it is. So that's what a one-sided limit is. You can do it graphically, you can do it analytically, doesn't really matter. But that allows us to get into a kind of a big deal. It gives us into the idea of continuity. So when is a graph continuous at a point? So let's say f of x is continuous at x equals c if 3 conditions are met. Takes 3 conditions. First condition, f of c has to be defined. The second one, the limit, and I'll have to go back in here and write it in a second for you, exists. And not just do they have to be defined, the function value be defined, the limit exists, they also have to be equal to each other. So these are our three characteristics that always have to be true in order for something to be continuous at a particular value. Notice, we're only dealing with a specific value here. We're only dealing with one value of x. We're not dealing with the entire function. We're dealing with one value of x. So if we go back to our last value here, or the last problem we just dealt with, and I just want to look at it briefly here. For this one right here, we were able to go through and we were able to prove that the limit existed at x equals 1. So I'm not going to go through and do all that over again. But, so I would have met one of the qualifications, but it has to meet all three characteristics. However, if I were to plug 1 in here, notice this right here is less than, this is greater than. I don't have anything that when x equals 1. So this would have been undefined. And since it's undefined, even though the limit existed, but the function is undefined, we would have then gone back and said, that f of x is not continuous or discontinuous. You can use either one you want. At x equals 1 because, and then we say what we did. F of 1 is undefined. So when we're trying to deal with continuity, we're dealing with three parts. We've got to deal with the limit, we've got to deal with the function value, and then we need to make sure that we check to make sure that they are actually the same. So even though that last example we dealt with, the limit did exist and was equal to a value, it was not defined. Notice, again, limits exist or don't exist. Function values are defined or undefined. There is a difference between them. So let's have you guys try one of these here. Let's see what you can do with this one. F of x equals, let's call this sine of x plus 3. Where x is less than 0. And we have 3 minus root x. If x is greater than 0. Why don't you guys go ahead and take a little shot at that and see if you can prove using the three characteristics that the graph is continuous when x equals 0. All right, so that's what we're trying to do. Is f of x continuous when x equals 0? All right, so hopefully you guys had a chance to kind of play with that a little bit. So to begin with, I need to first determine, is it defined? Is f of 0 defined? I'm going to make that line a little bit better. That did not come out well. So I see my line here. So that means I'm going to use that particular value here of the piecewise. Is f of 3 defined? And we would say, yeah. F of 3 is defined. We've got the first part. And now we're going to prove, does the limit exist? So this gets down to what we just talked about, the one-sided limits. Do the one-sided limits agree? Are they equivalent? So we're going to first take this from the negative side. And I don't actually have to write the sine x plus 3. I can go ahead and just plug it in there. So sine of 0 plus 3, that equals 3. And then even though I've already did this one when I was doing the function value, I still got to write the notation for it. So, and that would be, not that, 3 minus root 0, which would be 3. So, since they're the same, that means that it exists and that it equals 3. So what we're doing here is we're doing a lot of notation here, and we have to make sure that our notation is correct, because that's what the College Board is going to be grading us on. Is our notation correct? Can we reason well? All right, and really, you guys are math scholars now. You want to make sure that you reason well. So again, it's not just can you get the correct answer, it's can you reason why, be able to explain it why. So notice my notation here. Notice on these limits, I'm making sure that I include f of x. A lot of you guys are going to just drop the f of x here. That is no good. Got to keep that f of x all the way. All right, so we did our first two parts. It was defined, it exists, and then the last part, do they agree? And in this case, they do. We know that. So since f of 0 equals 3, which equals the limit at 0 of f of x, then, so since they're equal, then I can go ahead and write where it is. So I'm going to go ahead and flip over here so I can write a little bit quicker. Then f of x is continuous at x equals 0. Notice the process. We first start off with it being defined. So we have to deal with the definition of it, the function value being defined. Then from there, we had to deal with, does the limit exist? Well, it did exist. And then the last part is, are they equal? At any point, if it fails one of these three characteristics, then our function is not continuous at that x value. It has to meet all three characteristics. And if it does, then we have ourselves a continuous function. So we said before that there are two different types of discontinuity. If it's not continuous, so we want to prove things continuous, but sometimes they're not continuous. And that brings us to the types of discontinuity. And we've talked about this already. We had two types. We had removable points of discontinuity And the reason we call it a removable point of discontinuity is because we could set up a piecewise function to essentially fill in the hole. And we have a non-removable. Continuity. There we are. So a removable point of discontinuity, and we talked about this already, but it's worth repeating again. A removable point of discontinuity is when the limit exists, but the function value is undefined. In other words, it's a hole. So removable point of discontinuity. This exists when the limit exists, but f of c is undefined. And we said that is a hole. A hole is a type of, or is our removable point of discontinuity. Now, we don't call it a hole anymore. We don't say that this is a hole. We say that is a removable point of discontinuity. Well, we have one removable point of discontinuity. Now, for non-removable point of discontinuity, there were three. The first one is the one most people think of, the vertical asymptote. So the graph comes up, never reaches it, graph comes down, never reaches it. So this one, the limit doesn't exist. All right, and then the other one that a lot of people like to think about is when at some value of c, at whatever that value is, when the graph goes to two different y values. In other words, the one-sided limits don't agree. So these right here, this is when our limit doesn't exist. The other type of removable or non-removable point of discontinuity is when our graph, and this was kind of the weird one, we saw this on an example a couple days ago. It has a function value, so the function value exists, but the limit doesn't meet it. So this is the other removable point of discontinuity. And this exists because the c value doesn't equal the limit value. So when you're looking at removable points of discontinuity, this is essentially what you're looking at. If the limit exists, but the function value is undefined, in other words, a hole, that would be a removable point of discontinuity. Every other discontinuity is non-removable because the limit doesn't exist. In this one, it's because it goes to positive or negative infinity. It's unbounded. This one, because the two one-sided limits don't agree, they're not equal to each other. That means the limit does not exist in both cases. Or if the limit and the function value aren't equal, then it's also non-removable. So we have our different types of discontinuity. And so as you guys are going through here, you're going to have to deal with the various types of discontinuity. So let's take a look, see at that just to see if we can't figure it out here. Determine the values of x where f of x is discontinuous. Determine the type of discontinuity for each of those values. All right, so let's go ahead and put an equation up here then. Say I give you a problem like this. So let's go f of x equals x minus 2. And let's go with x squared minus 4. Actually, we can do a little better than that. Let's make it x squared minus 3x plus 2. And we have x squared minus 4. So our points of discontinuity are going to exist when our denominator here is equal to 0. And again, we would want to use the limit definitions to help us out with this. But in general, if I'm looking at this graph and I were to simplify it down, notice that this function value, I'm going to shorthand it here just because I want us to be able to see what those types of discontinuity are. So we can, if we factor this out, notice what we have here. We have the function x minus 1 and x plus 2. But also that x can't be equal to positive 2. So the type of discontinuity we have here is, well, we have two different types. And let's see if we can't go through a little bit of detail and figure it out here. We have a removable point of discontinuity at x equals 2. And we have a non-removable point at x equals negative 2. But why is that? That's a pretty color. Well, if we were to go through and do the limit for this, in other words, if we were to have gone through and do the limit for f of x at 2, we would have started off plugging it in here. And we would have found out that it was 0 over 0. And then by rewriting it, and factoring out that factor, I could have proven that the two one-sided limits would have been equal to 1/4. So the limit would have existed even though the function itself was undefined. So we would have been able to evaluate a limit, so we could have found a limit, but the function value itself would have been undefined. That would have made it a removable point of discontinuity. Whereas over here at negative 2, if I were to plug this in here, right from the very beginning, I would add x squared minus 3x plus 2 all over x squared minus 4. Notice I would have got 4 plus 6 plus 2 all over 4 minus 4, which would have been 12 over 0. It wouldn't have been dealing with a value that I can rewrite because it's not indeterminate form. Indeterminate form is a very good chance that there is a removable point of discontinuity. Well, this isn't indeterminate. Therefore, this would have been a non-removable because the limit here of f of x does not exist. So when we're dealing with removable points and non-removable points, it all has to deal with our characteristics. If the limit exists, but a function value is undefined, then it's removable. If the limit doesn't exist, or if the limit and the function value aren't equal to each other, then it's non-removable. And this leads us to our very last idea. And it's a huge idea. There's only a few different abbreviations we can ever use in calculus, and this is one of them. It's called the intermediate value. Also called the IVT. What this theorem does is that it allows us to verify if a function value is defined. So if I ever ask you if a function value is defined, you are using the intermediate value theorem. And here's essentially what it says. It says if f of x is continuous on a closed interval from a to b, so two random values, and f of a does not equal f of b. I'll have to fix that in a second. Also, if k is between f of a and f of b, then there is at least one number x equals c between a and b, such that f of c equals k. All right, so that sounds really, 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 really wordy. Really wordy. Let me see if I can't explain it to you in a visual way, and then we'll see how this actually applies. Say I have a value. We'll call that A, we'll call that B. Now this theorem is called an existence theorem. And the reason why it's called an existence theorem, by the way, I'm going to put f of a down here, but f of a could have been on top too. Where I put those don't really matter. It's called an existence theorem because it just shows whether or not something could be there. It doesn't tell you if it is there, it just tells you if it could be there. So this is saying that I have a function that's going to be continuous between a and b. I'm going to have some c value between them. So we'll call that c. And we're going to call this right here, we'll call this k. So our existence theorem says that k is between our two y values, and that c is between the two x values. If it's continuous, so the graph has to be continuous. It has to be closed. And that, in other words, They're closed dots, so it's continuous. There are no points of discontinuity in here. And if there's no points of discontinuity in here, that means the graph has to somehow be connected the entire way from our point on the left to our point on the right. So we don't know where it goes, but we know that it's continuous as it gets up there. What this existence theorem says is that means that there has to be at least one value, one time, where that graph is going to be equal to that k value. And that k value, that would be the value of c. So in other words, our c value would have been over here. That's not weird. I'll do that. Just want to move it. Apparently can't move it. That's weird. Oh well. No, I want to delete it. I don't know if I can. Anyways, let me see if I can. I'm just going to rewrite the c value because apparently I'm not smart enough to move the dumb thing. There we are. C is right there. All right. So in other words, there's going to be some x value between a and b such that it's going to be equal to that k value that's between f of a and f of b. It doesn't tell us what that c value is. It just says it exists, and if you want to look hard enough, you can find it. So how does this work for us? Well, it does this. Verify that an x value, x equals c, exists from 1 to 3, such that f of c, f of such that f of c equals 0. In other words, can we prove if it has an x-intercept? So we need to give ourselves some f of x function here. So again, you would be given the f of x function. You wouldn't have to make that up. So I want you to verify if it exists for the function, let's go x squared minus 4. And over x plus 1. That'll work. So is there an x-intercept somewhere between x squared minus 4 and x plus 1? Well, let's think about it. When is f of x discontinuous? So the only value that x can't be is -1. So x is going to be continuous between 1 and 3. It's only not continuous at -1. So we know that it is continuous. So it met the first part. Now it needs to meet the second part. Is it between, is our k value between f of a and f of b? So this is our k value. Is it going to be between f of a and f of b? So we got to figure out what those are. What is f of 1? Notice we're not figuring out the x value. We're just proving or trying to determine if it exists. So if I plug 1 in here, I get -3 halves. If I plug 3 in here, I get 3 squared minus 4 all over 3 plus 1. And when I get that, solve that out, I get 5/4. So I'm going from a negative value to a positive value. Well, of course, 0 is between a negative value and a positive value. So this intermediate value theorem is going to say that a value exists. Doesn't tell me what the value is, but it tells me that the value exists. Since f of x is continuous from 1 to 3, and f of 1 is less than or equal to, I'll have to add that in a second, to 0, which is less than or equal to f of 3. Then by, always got to say why, then by the IVT, there exists some x equals c from 1 to 3 such that f of c equals 0. Notice, it didn't tell me what the value was. That's so huge here. It does not tell me what the value is. All it does is it tells me that the value exists. I know that it's continuous from 1 to 3. I know that 0 falls between my two y values. Then the IVT says that there exists. Now, if I wanted to figure it out, I could, but that's not what it's asking me to do. It's not asking me to plug 0 in here and then solve it. I could do that to figure out where that value is. And if I were to solve it, I'd find out that f of x equals 0 when x is -2 and when x is +2. So I would find that there was at least one of these that worked. Notice the -2 falls outside my domain that I'm dealing with. So it wouldn't have met that condition. But the +2 was in between 1 and 3. So it guaranteed that there was going to be at least one x value that did work. Doesn't tell me what it is. It just tells me that it exists. And like I said, this is a big idea. You will have a couple of these, one or two of these on your multiple choice. You'll get one of these on your free response. So I'd like you guys to try doing the same process over again. Verify that some value x equals c exists from -1 to 4 for f of x equals, and I'll tell you what it equals here in a second, such that f of c equals 5. And the value that I'm going to give you here is going to be x squared plus 7 and x plus 2. I want you guys to go ahead and pause the video and see if you can determine if the IVT works, if there is a value that will be equal to f of 5. All right, well, I'll tell you what, guys, I'm just going to, whenever I'm doing an IVT problem, I'm essentially writing the same statement over and over again, so I'm not even going to bother erasing it. I'm going to leave it there. So first thing I got to deal with, do I have a value that's continuous? The only place where my function is discontinuous is at -2. So that means my graph is, or my function is continuous between -1 and 4. And then I also need to figure out what f of -1 and f of 4 is. So if I plug -1 in here, I get -1 squared plus 7 all over -1 plus 2. And that would end up being 8 over 1, which is 8. So that means f of 4 better be less than 5, so 5 falls in between. Whenever you're asked to verify a function value, you're being asked to do the IVT. Right here, this is a big idea right here. You want to star this somewhere in your notes. Whenever you're asked to verify a function value, that is the IVT. Get back here in a second. There we are. 4 squared plus 7, and then we have 4 plus 2. And that would be 1623 over 6. And that's just a little bit less than 4. So my IVT works. Watch this. I'm not even going to bother even rewriting it. So since f of x is continuous from -1 to 4, and what was my smaller value? That was the f of 4 this time. And this should be f of -1. Then by the IVT, there should be some x value from -1 to 4 such that f of c is equal to 5. Still the same. Nothing changed. It's still the same statement. That's the intermediate value theorem. This is one that you want to put a big giant star next to in your notes, whatnot. This is one you're going to use quite a bit on the AP test. All right, it's a big, big theorem. We use it to prove a lot of existence ideas in upper level math. We use this theorem a ton. It's very hard to prove, actually, but it is an extremely important theorem for us. So, all right, gang, good luck on your notes. One-sided limits, continuity, and the IVT. Take care.